Here we have a series question that you might see on the BC exam. This one is definitely pretty tricky. So intuitively, it's kind of like a p-series. But it's not. But it's kind of like one. So it's like in the denominator we have like some power of n, but instead of it being just a power of n, it's a power of n times a power of the natural log of n. So natural log is really, really slow. It's slower than any root even. So this is kind of like n to the 1 plus something. It's like a little bit smaller than 1 over n. But as we know, 1 over n is the toughest one. 1 over n is like the boundary point. You know that 1 over n diverges, but even a little smaller than 1 over n converges. But this one's like right on the boundary, so it's kind of hard to tell just thinking about it like that. So the first thing that I thought to try was the ratio test. Let's try going through that. The ratio test says you take this term. Well, first you plug in n plus 1. So you plug in n plus 1 squared like that. And then you multiply by the reciprocal of the original. So n times ln of n squared. And then you try and simplify that. Well, you want to put everything that's like the same type of thing together. So I'm going to put the n with the n plus 1. And then I'm going to put the natural log of n with the natural log of n plus 1. And then since they're both squared, I'm just going to write the square like that. And now we got to take the limit as that goes to infinity. Well, this left thing is definitely just 1. And it's kind of, well, it's good to just know already that the natural log of n divided by the natural log of n plus 1 also goes to 1. So this whole thing goes to 1, which unfortunately means the ratio test fails to tell us the result. So the ratio test is not the way to go. So perhaps instead we could do the integral test. The integral test says we can just replace this with the integral over the same bounds of the same function, but of a continuous variable, so x instead of n. And we're just taking the integral of that like that. And I think this is going to work. We need a certain substitution to make this happen. We can let u equal the natural log of x, because then du is 1 over x dx. And I've got my 1 over x dx right here. So we should be good to go on making that work. All right, let's give this a try. This is going to be the integral of 1 over u squared du. Right, because this became our du here, and then this is u squared, so that's just 1 over u squared du. And then watch out, because our bounds are still in x, so we got to convert them. That would be the natural log of 2 and the natural log of infinity, although that is just infinity. Okay, so then fortunately we can take the antiderivative of that. That's, well, I always got to think of it as u to the minus 2, and that helps me to realize that that's negative u to the minus 1 from the natural log of 2 to infinity. And then when we plug stuff into there, that's going to be negative 1 over infinity minus negative 1 over the natural log of 2. 1 over infinity is 0, so this becomes plus 1 over the natural log of 2. Now, it doesn't actually matter what specifically it comes out to. The point is it comes out to be a finite number. So that means that this integral is finite, which means that this series is finite. So it turns out that this series converges by the integral test.